All right, so in this video, we aren't going to be doing a whole lot of practice problems. I'm just going to be listing out all of our important derivative rules for calculus. So I'm going to start off with our general derivatives. So very beginning, if I want the derivative of a constant, so let's say that f of x equals 3, right? 3 is evidently a constant. There's no x, there's no nothing. This is just one number that stays the same. So if I take the derivative of this, the derivative of a constant is 0. That's our first one. The derivative of a constant is always 0. Our next one is the derivative of a function that has a constant coefficient, which is slightly different. So let's say I have a function named g of x, and let's say we've got a constant, c, times f of x. That's what this equals. If I want the derivative of g of x, because this is a constant coefficient, it doesn't change. It stays the same, and I'm just taking the derivative of whatever f of x is. A good example of this is maybe g of x equals like 2x, like 2 times x, right? In this case, our g prime of x, it's going to be 2 times whatever the derivative of x is. In this case, the derivative of x is just 1, so our answer ends up being 2. But it's 2 times the derivative of x in that case, because x is our f of x in that case. I hope that makes sense. Let's keep going. One of the most critical things that we're going to be using is what we call the power rule for taking our derivatives, which just says that if I've got, I'll say g of x again, if I've got a function and I've got x to some power n, right? If I take the derivative of that, I'm going to take my power and turn it into my coefficient. So it's going to be n times x, and now our power changes. We just subtract 1. So the derivative of this is that power in front times x to that power minus 1. So another example of this, let's say g of x equals x to the third, right? So in this case, g prime, we bring that in front. That's our new coefficient. So 3 times x to the 3 minus 1, or just x squared. Let's try, and we could always, I know that we kind of really hate the limit definitions, but we can always try those limit definitions, right? Because we know that the derivative of something is the same as the limit as t approaches x of f of t, so in this case, t cubed minus f of x over t minus x. And I could factor that out, so that would be the limit, let's see, that's a tricky one. Oh, no, that's one of our perfect cubes, so it's going to be t minus x, and I believe that should be t squared plus tx plus x all over t minus x. Those cancel. This turns into the limit of this, which, oh, I feel like I messed up. Oh, that should be an x squared. Sorry. So then if we plug in that x wherever the t goes, that gets us t squared, or sorry, no, x squared plus x times x, which is another x squared, plus x squared, or 3x squared, which is exactly what we got for our derivative here. So the power rule is just a shortcut for all of this. And all of our derivative rules really are. They're just a shortcut for finding the derivative using these limits. But it's still good to understand how those limits work, just because we do end up using limits a lot later on in calculus. We just don't use them a whole lot for our derivatives once we learn those shortcuts. but nonetheless, still good to understand. Let's try now. Let's see. We've also got our sum and difference rules. So the sum rule just says if I have a function f of x, maybe I've got f of x equals x squared plus 2x plus 1, right? So the sum rule just tells me that the derivative of this whole function is the derivative of each part that I'm adding. So it's just the derivative of x squared, which would be 2x because of our power rule, plus 2, because this is also because of the power rule, actually. Let me pause. 2x is the same as 2 times x to the first power, right? Because anything to the first power is just itself. So using our power rule, we put that 1 in front, so it's a 1 times a 2, and then we subtract a 1 there, so it turns into an x to the 0. So 1 times 2 is 2, x to the 0th power is a 1, so we just get 2. And then, like we said before, the derivative of constant, and 1 is a constant, is 0. So it basically just kind of drops off. So the derivative of f of x is just 2x plus 2. And that's all our sum rule shows us. It's that if we have different terms that we're adding and we want the derivative of that whole thing, we just take the derivative of each term and add them back together. The difference rule is the exact same thing, except we're subtracting, right? So they're technically listed as like two different things in our textbook, but if I was subtracting up here, I'm just going to keep subtracting down here, and I get the exact same thing. Or I go about it the exact same way, rather. Starting to get into some of our trickier derivatives, for our general ones anyway. These are still our easier ones. We've got our product rule, which I know I definitely mention some of these in problem set 7, and when I do problem set 8, there's going to be a lot of chain rule in that one. But the product rule is for if we have the derivative, if we want to find the derivative of two things that are being multiplied. So when we said, like, if we have a constant coefficient, our constant doesn't change. This is different because it's not a constant. So this is if I've got maybe, for example, I've got an x squared times, let's say times 2x, right? Obviously right now I could multiply that out, but that's besides the point. If I'm multiplying these, if I want to take the derivative, then in this case I could multiply that out like I just said, and then I could use the power rule. But for a lot of cases we can't do that necessarily, or it's really difficult to. So instead we use the product rule, which tells us that we take our first term times the derivative of our second term. So this is our first term, this is our second term, and then we add that to the derivative of the first term times the second term. So let's see, our u is x squared, so it's going to be x squared times whatever the derivative of 2x is. And we know the derivative of 2x using our power rule is just going to be 2. So our first part here is that first term times the derivative of the second term, or just x squared times 2. And then we add that to the derivative of our first term, which using our power rule we can find is a 2x. And then just times our second term, which is 2x. So this becomes a 2x squared plus a 4x squared. And obviously we can combine that. That is a 6x squared. So our derivative in this case is 6x squared. And if we were to multiply these together, right, if I went ahead and multiplied them like that, because I can combine them because they're both just x's, that would get me a 2x cubed, right, because that's just combining like terms. And then if I take the derivative of that using our power rule, I get the same thing. So we can always double check it with that. The product rule is particularly useful when we have much more complex functions, or complicated, I should probably say. So just when there's a lot more happening. For example, let's say f of x is equal to, we'll say maybe x squared plus 4 times maybe x minus 2, right? Again, I could FOIL this out, or I could take this chunk here as my first term and this chunk here as my second term, because I see I'm multiplying those. Which gets us, I would take the derivative, or I would take this, and it would be x squared plus 4 times the derivative of our second term, which is just 1, actually, lucky us. Then I add it to the derivative of this term, which would be a 2x, times this term. And so this would be that derivative there. Obviously, I can like FOIL out, combine like terms, and have it be a little less lengthy, but sometimes it's just easier to leave it large like this. It's also really good to know the power rule for when we don't actually know our function. So maybe my f of x is equal to these two functions multiplied, right? If I don't know those functions, all I know is that my derivative of f of x is going to be my first term, so g of x, times the derivative of h of x, plus the other way around, right? So the derivative of g of x times h of x. But moving on, let's get now into the quotient rule. This one's a bit trickier. This one's a harder one to remember, unfortunately. So our quotient rule, let me just write that up here. Quotient rule. Our quotient rule is when we've got terms that we're deriving on top of a fraction and on bottom. So let's say f of x equals, for example's sake, I'm just going to use two functions we don't know yet. So I've got a function g of x divided by a function h of x. Well, our quotient rule tells us that the derivative of the whole thing is going to be this bottom term times the derivative of our top term minus our top term times the derivative of our bottom term, all over the bottom term squared, or times itself, right? And obviously there's a lot going on there that's really tricky to remember. The way that I learned it in high school, my teacher, I don't know if it's super helpful, but the way that I learned it is we say low d high minus high d low over low low, which just tells us that we take low, our low term, times d high, so the derivative of the high term, minus high d low, so the high term times the derivative of the low term, over low low, so the low term times itself. That might not be helpful, might just be easier for you to try and memorize this, but this is how I personally remember it, and you'll probably see me writing this out a lot when we use quotient rule, just because it helps me personally. Let's try an example of quotient rule to try and drive that home. So let's say, in this case, f of x, maybe it equals like x squared minus 1 over x cubed, right? In this case, we would have to use the quotient rule because we've got an x up here and an x down here, so we have to use quotient rule to figure it out. We could use the product rule technically, but we don't need to worry about that right now. So in this case, we've got our low term, right? So it's going to be, here, I'll actually write this part out. So it's going to be our low term times the derivative of our top, and the derivative of x squared minus 1. Well, this is a constant, so it disappears because it equals 0. And this we just use our power rule for, so it's going to be a 2x. So we've got our low times the derivative of our high minus our high, so x squared minus 1, times the derivative of the low, apply that power rule, all over low low. So this times itself. And then we could, distribute those out. So we'll get 2x to the 4th minus, let's see, that'd be 3x to the 4th plus 3x squared, all over x to the 6th. And then combine like terms, so that's a negative x to the 4th plus 3x squared over x to the 6th. And we could actually factor and cancel. Obviously, you don't have to worry about this too much right now because I'm just solving an example, but I'm actually going to factor out, I'm going to factor out x squared. So it's going to be negative x squared plus 3 over x to the 6th. That cancels out and that goes down to a 4. So our answer is negative x squared plus 3 over x to the 4th. But all we really need to focus on right now is the rule. So this bit up here, again, this is just an example to help us kind of see that application a little bit. And then we've got one more of our basic derivative rules, which is chain rule, also known sometimes as the inside-outside rule, which I know a lot of kids at my high school would call it the inside-outside rule because it helps them understand it conceptually. And so the chain rule is for if maybe I've got a function, and it is like a function within a function, right? So maybe I have g of h of x. We could also write that as, I believe we can also write it like that if that's a notation you're more familiar with, but this is how I write it. So we've got g of h of x, and we want to take the derivative of this, and the trick is that there's this term in here that also needs the derivative taken of it. So what chain rule tells us is that the derivative of this whole thing is going to be the derivative of the outside with the inside unchanged times the derivative of the inside, right? So we took the derivative of g and we kept the h of x inside, and then we multiplied it by the derivative of h of x. A good example of this is maybe I've got f of x equals, maybe I've got x minus 2 to the 4th, right? I could like FOIL that out, distribute that, multiply it, and then use my like sum rule and whatnot. But we could also just use chain rule here. In this case, our outside term is, our outside term is something to the 4th. So I'm going to write that as u to the 4th. Sorry, no. So, sorry, this one's trickier to explain. So I'm going to call this whole thing u, and I'm going to say that equals some term v to the 4th, with v being this inside bit, right? V, like we just said, is going to be that inside bit. So now I know that the derivative of u, I'm going to write that as u prime, like this. I know that that's going to be whatever the derivative of this is, right? So it's going to be 4 times v to the 3rd because of our power rule. I'm going to move the page. But I know because I also have a derivative of that inside, I'm going to multiply it by the derivative of that inside, right? So it's the derivative of the outside times the derivative of the inside. In this case, the derivative of our inside is just 1 because it's an x minus 2. So this turns into 4 times x minus 2, right? Because that's our v still. That was our inside to the 3rd times 1 because that's our derivative of it, which means that f prime, so our derivative of f, is going to be this. Another example might be, let's give ourselves a slightly more complicated one. Maybe I've got a couple different functions nested inside of each other, which is why we'd want to write all of that out. So maybe I've got, let's say, an x squared minus 1 to the 5th plus 5 all to the 3rd, right? So now I've got 3 things inside of here. So I'm going to go ahead and I'm going to just use my u again to define this whole thing. So it's going to be u equals, we'll call all of this v to the 3rd, right? And we know that the derivative of u is going to be our power rule, and then times whatever the derivative of v is. Like we just said, v is all of this inside of here, but because I see that there's more stuff in there, I'm going to use another variable here. So I'm going to say that v equals, we'll call that c, so c to the 5th plus 5, right? So my derivative of v, let me move this over, is going to equal, again, use that power rule, and don't forget to multiply by the derivative of c there. And then we know the derivative of a constant is 0, so it's just plus 0 or nothing. We don't actually have to write that. And now c is our final little term in here, which is that x squared minus 1. I know c prime, the derivative of c, is 2x because of my power rule, and the derivative of constant is 0. So now I just go backwards and I plug that in. So the derivative of v is going to be 5, let's see, c was x squared minus 1 to the 4th times the derivative of c, which is 2x, okay? And now we take that, because this is our derivative of v, and we plug that back into here. So our derivative of u is 3 times v, and v was c to the 5th, so that's going to be that x squared minus 1 to the 5th plus 5 squared, and then times the derivative of v, which we found was this. So it's going to be times all of that. Yeah. So what we just found is that in this case, the derivative of our f of x is all of this, and I could combine bits and pieces of that. I'm just going to write most of it as is, honestly. And then I'm actually going to combine that bit, so it's going to be 10x. So it's all multiplied, so I can do that. And there's our derivative. And we see how complicated that was. That's why we have to use chain rule, and that's why we want to write out all of our steps, because that's much harder to do in our head, right? It's not super intuitive sometimes. But yeah, so that's our chain rule. Not my favorite, not most people's favorite, I think, just because there's a lot going on there. I personally hate just how much writing it is. Give me one moment. Does not want to erase everything. Okay. All right. Now we're going to move out of our general trig rules, our general derivative rules, and into our trig derivatives. So this one is hard for me to come up with examples for, just because it's kind of, I tell you them, you memorize them. But so we have derivatives for all of our trig functions. So if I want to take the derivative with respect to x of sine of x, the derivative of that is going to be cosine of x. So the derivative of sine is cosine. Similarly, the derivative of cosine of x is a negative sine of x. Moving down the line, we've got the derivative of tangent, which this one is a secant squared, which is one of the more difficult ones to remember. Then if I want the derivative of secant, that's actually going to be secant times tangent. Then I've also got, let's see, I've got cotangent is going to be a negative cosecant squared. Just like the derivative of tangent was secant squared, the derivative of cotangent is a negative cosecant squared. And then finally, we have the derivative of cosecant is going to be a negative cosecant cotangent. Again, just like secant becomes secant tangent, cosecant becomes a negative cosecant cotangent. I don't know if that helps anybody, but that personally helps me trying to remember them because it's a little bit of a pattern there. Another noteworthy bit is that you'll notice that all of the ones that start with a co in the name, right? So cosine, cotangent, cosecant. When we take the derivative, those are all going to be negative. I often forget the negatives personally, so that's I feel like that's something important to point out. These are always going to be negative. And the easiest way to remember that is because they all start with the C, that co sound. And those are all of our basic trig derivatives. You could then apply those alongside of our other derivative rules. So maybe I have a function, maybe I've got like 5 times sine of x. If I want to take the derivative of this, well, I know that that's a constant coefficient, so it doesn't change. So it's just 5 times whatever the derivative of sine is. That's going to be cosine. Or maybe we've got something a little bit more complex. Maybe I've got, f of x equals sine squared of x. Well, in this case, we'd actually have to use chain rule. We could technically use product rule because that is the same as sine of x times sine of x. But we'll use chain rule just because that's a little bit easier, I think, personally. I'm used to using chain rule here. So our outside term, our u, is v squared, and our v is just sine. So we take the derivative of our outside. So it's derivative of the outside times the derivative of the inside. The derivative of the inside, in this case, would be a cosine. So, So it's going to be 2 sine squared of x times cosine of x, right? Because this is from our power rule. This is, no, this should not be squared still. It should just be sine of x. So 2 sine of x times cosine of x, because we took that power rule. We did 2 minus 1 for our power there. And then we multiplied by the derivative of our inside. All right. Again, I know it's pretty tricky and there's not really many tricks or tools to help us with this, but you really do just have to memorize the trig derivatives. At the very least, just memorize these and probably that one. The derivative of cosecant and cotangent don't come up too much generally. Still good to remember them, obviously, but these other 4 are the ones that are the most common in my experience, most particularly sine and cosine, of course. Okay, now let's work on, very briefly, this is a pretty short one, is our derivatives of logs and exponents. So if maybe this function equals, I don't know what happened there. If I have a log with a base of b of x, the derivative of that is going to be 1 over the natural log of whatever my base is times whatever x is. So a good example of that, let's say I've got g of x equals a log with a base 2 of, let's say, 2x. So our derivative should be, I believe it should be natural log of 2 times 2x. That's all that is. And we see that applied later. A lot of people teach this derivative rule separately from the derivative of natural log. However, let's say we've got like natural log of x, right? The derivative of the natural log of x, you'll learn, is just 1 over x. But if you ever forget that, I would focus on just remembering this rule because you can figure it out through that. Just because natural log is just a log with a base e of x, right? So if I use my other rule, I know that the derivative of that is going to be 1 over the natural log of my base, in this case e, times x. Natural log of e is 1, so it turns into a 1 over x, right? Because 1 times x is just 1. Or sorry, it's just x. And that's kind of where this comes from. You'll see a similar thing here in a moment when I go over the derivative of exponents. So we know how to take derivative of this with our power rule, but slightly more difficult is, say we've got this. We've got a to the power of x, where a is a constant, right? So it may be like 2 to the x or 7 to the power of x, right? If we want to find the derivative of a to the x, that's going to be itself times the natural log of whatever a is. So if I have 2 to the x, the derivative of this. So if I have 2 to the x, the derivative of 2 to the power of x is going to be to the power of x times the natural log of 2. This is also where our derivative for e to the x comes from, because it is just itself, as I believe we've learned already. And the reason that is for a similar reason as with our log exponents, just because if we have derivative of e to the x, that's the same as e to the x times a natural log of e, just like our rules up here, right? Because e is our a in this case. But natural log of e is just 1, so it turns into e to the x times 1, or just its original self. It is important to note, it's a really easy way to slip up sometimes, is if I have maybe e to the 2x, right? Because the derivative of e to the x is just itself, a lot of people would think the derivative of e to the 2x is just e to the 2x, but that's not the case. In this case, we would have to apply the chain rule, or even, maybe technically even the power rule, but we can apply chain rule here. So I've got my outside is an e to the v, right? So my derivative there is going to be my inside times the derivative of my outside, which in this case is just itself. My inside being that 2x, its derivative being 2. So its derivative would actually be 2 e to the 2x because of how our chain rule works. But that's it. That's all that there is to our derivatives of logs and exponents. I know those are pretty tricky to remember, but and that they're often taught as like 4 different rules, but it's really just 2 rules. And if you can remember, again, if you can just remember that the derivative of this is 1 over natural log of b times x, and you can remember that derivative of this is this, then you can figure out the ones with e if you don't always remember those. But really try to remember these 2 rules at least. All right, and then our very last thing, I don't know when we're actually going to get to it in class. These are my personal least favorite derivative rules, especially when we get into integrals going backwards from them. They're just hard to recognize. But this is going to be our inverse trig rules. Inverse trig derivatives. And again, this is kind of just, I list them, we remember them. It sucks, but it is what it is. So the derivative of inverse sine of x, or you might have heard this as arc sine, right? So this is the same as arc sine. Is that inverse sine? So the derivative of inverse sine is going to be 1 over the square root of 1 minus x squared. Luckily for us, the derivative of arc cosine is the exact same, but negative. So it's a negative 1 over square root of 1 minus x squared. And you'll see a similar pattern like that as we go down. So let's try now the derivative of arctangent, right? And that's going to be 1 over, I believe it's just 1 plus x squared. And then similarly, the derivative of inverse cotangent is exactly that, but negative. So 1 over 1 plus x squared, but negative. Now, let's say we've got the derivative of inverse secant. It's a fun one. That's going to be 1 over x times the square root of x squared minus 1. And then the derivative of cosecant, oops, wrong one, of inverse cosecant, sorry, is the exact same, and once again, negative. So negative 1 over x times x square root of x squared minus 1. Yeah, so we've got sine and cosine. Cosine is the same but negative. Tangent and cotangent. Cotangent's the same but negative. And secant and cosecant. Cosecant's the same but negative. Once again, the ones that start with our co sound are negative, if that helps. I don't really have any examples for this one. I don't think that we're going to be dealing with them for a while. Probably not until we're closer to working on integrals. So that'll be a good little bit of time from now. But it's still good to take notes on them, try your best to remember them, come up with any tricks if you can. But yeah, I believe that is all of the derivative rules that we're going to go over today. I can't think of any others that I want to bring up. And those are kind of our building blocks for calculus. All those derivative rules and limits. But yeah, so that is it, and I hope that this video is helpful. Thank you for watching.